The hypothesis that we live on or within an atom is intriguing because it challenges our perception of scale and reality, drawing on principles from quantum mechanics and cosmology. In quantum mechanics, particles such as electrons exhibit behaviors like wave-particle duality and quantum entanglement, which suggests that even tiny particles contain complex structures and interactions. Analogously, our universe could be an atom within a vastly larger structure, governed by similar laws at different scales. This idea is supported by the concept of fractals, where patterns repeat at every scale, and the nested nature of our reality, where smaller systems resemble larger ones. While this hypothesis remains speculative, it pushes the boundaries of our understanding and invites us to consider that the vastness of the cosmos might mirror the intricacies of the atomic world. Here are detailed examples to further illustrate the hypothesis that we live on or within an atom: electron orbits and planetary systems. Example: in our solar system, planets orbit the Sun due to gravitational forces, much like electrons orbit the nucleus of an atom due to electrostatic forces. If Earth were an electron, it would have a defined orbit around the nucleus, just as it does around the Sun. The quantized nature of electron orbits in atoms, where electrons can only exist in specific energy levels, could be mirrored in the stable orbits of planets. Quantum tunneling and macroscopic movement example. Quantum tunneling allows particles to pass through barriers that they classically shouldn't be able to. For instance, in a semiconductor, electrons can tunnel through an insulating barrier, enabling modern electronic devices. If we lived within an atom, similar tunneling effects could explain why celestial bodies might suddenly shift positions in ways that classical mechanics can't explain. Entanglement and instantaneous connections. Example: quantum entanglement links particles so that the state of one instantly influences the state of another, no matter the distance between them. Imagine if galaxies or stars were entangled. A change in one could instantaneously affect another, similar to how entangled electrons behave. This could explain mysterious cosmic phenomena, like coordinated movements or unexplained gravitational effects. Fractals and self-similarity. Example: fractals are patterns that are self-similar across different scales, such as the branching of trees or the structure of snowflakes. If our universe follows a fractal pattern, the structures we see at the atomic level, like electrons orbiting nuclei, could be replicated at the cosmic level, like planets orbiting stars, suggesting that our planet could be part of a much larger atomic structure. Virtual particles and dark matter. Example: in quantum field theory, virtual particles constantly pop in and out of existence, affecting the behavior of real particles. This concept could scale up to explain dark matter and dark energy, where invisible, virtual components influence the dynamics of galaxies and the expansion of the universe, similar to how virtual particles influence atomic interactions. Russian nesting dolls and nested universes. Example: think of Russian nesting dolls, where each doll fits perfectly within a larger one. Our universe could be one of these dolls, an atom within a larger universe. Just as each doll is part of a set, our universe could be part of an infinite hierarchy of nested structures, each governed by the same fundamental laws of physics, but at different scales. Simulation hypothesis. Example: if our universe were a sophisticated simulation, the rules governing it would be programmed similarly across scales. Quantum mechanics, which describes the behavior of subatomic particles, could be the code that also dictates the behavior of larger cosmic structures. This simulation could make our planet an atom within a larger simulated reality, where the boundaries between scales are blurred. These examples show how the hypothesis that we live on or within an atom leverages the principles of quantum mechanics and cosmology, suggesting a fascinating and interconnected reality where patterns repeat at different scales and our perceived universe might just be a tiny part of a much larger structure. In the world of quantum mechanics, the familiar certainty of everyday life dissolves into a sea of probabilities. Here, particles don't behave like tiny billiard balls, but rather like waves spread out in space, their exact location and momentum shrouded in a veil of uncertainty. This inherent fuzziness, described by Heisenberg's uncertainty principle, dictates that we can never know both the position and momentum of a particle with perfect accuracy. The act of observing a quantum system inherently alters its state, blurring the line between observer and observed. One of the most mind-boggling aspects of quantum mechanics is the concept of superposition, where a particle can exist in multiple states simultaneously. Imagine a coin spinning in the air, neither heads nor tails until the moment it lands. That's the essence of superposition. A particle exists as a blurry combination of possibilities until an observation forces it to collapse into a definite state. At the heart of every atom lies the nucleus, a dense cluster of protons and neutrons, collectively called nucleons. These particles are held together by the strong nuclear force, one of the four fundamental forces in the universe. Orbiting this nucleus is a cloud of electrons, much lighter than their nuclear counterparts. These electrons don't follow fixed paths like planets around a star, but instead occupy regions of space called orbitals, where the probability of finding them is highest. These orbitals are quantized, meaning electrons can only exist at specific energy levels, much like climbing a ladder with distinct rungs. When an electron absorbs energy, it jumps to a higher energy level. When it releases energy, it drops back down, emitting light in the process. This intricate dance of electrons, governed by the laws of quantum mechanics, determines the chemical properties of atoms and their ability to form the molecules that make up our world. Gazing up at the night sky, we see a vast expanse sprinkled with stars, galaxies, and nebulae. But what if this cosmic tapestry, woven across billions of light years, has a much smaller, more familiar counterpart? Imagine for a moment that the nucleus of an atom is akin to a star, a dense, energetic core around which other particles orbit. Just as planets are held in orbit by the gravitational pull of a star, electrons are bound to the nucleus by the electromagnetic force. In this analogy, the vast distances between celestial objects mirror the relative emptiness within an atom. If we were to scale up an atom to the size of our solar system, the nucleus would be like a tiny marble at the center, while the electrons would be like grains of sand orbiting at a great distance. This comparison between atomic and cosmic structures might seem like a stretch, but it highlights a profound idea. The universe exhibits self-similarity across vastly different scales. Patterns repeat, echoing from the smallest to the largest structures we observe. The force that holds galaxies together in clusters, gravity, acts on an entirely different scale than the electromagnetic force that binds electrons to the nucleus. Yet, both forces follow an inverse square law, meaning their strength weakens with the square of the distance between objects. This similarity in behavior hints at a deeper underlying principle governing the interactions between objects, regardless of their size or the nature of the force at play. It suggests that the laws of physics discovered here on Earth might hold true across the entire cosmos. From the smallest atom to the largest galaxy, the universe whispers secrets through the language of mathematics. Scaling laws and dimensional analysis are powerful dialects in this language. Imagine the relationship between the surface area and volume of an object. As an object grows, its volume increases faster than its surface area. This principle affects everything from a mouse's metabolism to a star's collapse. By comparing ratios and identifying constants, we see the universe's common threads. Consider the force of gravity. It binds planets to stars and stars to galaxies. But does this same force govern the interactions between particles within an atom? At first glance, it might seem absurd. The distances are vastly different, the masses incomparable. Yet by applying scaling laws, we can explore the possibility of a universal force, manifesting itself differently across scales. We find that while gravity dominates on cosmic scales, the electromagnetic force reigns supreme in the atomic realm. The relative strengths of these forces, dictated by fundamental constants, shape the very nature of our universe. If gravity were stronger, stars would burn hotter and die faster, leaving little time for the emergence of life as we know it. In the vast cosmic ocean, the hydrogen atom might seem insignificant. It is the simplest element, with a single proton and electron. Yet within this simplicity lies profound elegance. Astronomers use distant stars to study physics, and we turn to the hydrogen atom for quantum secrets. The electron, bound by electromagnetic force, exists in specific energy levels like planets orbiting a star. These quantized levels are a quantum hallmark. Just as planets have specific orbits, electrons cannot occupy space between levels. When an electron transitions, it emits or absorbs light. This process, spectroscopy, helps us study distant stars and galaxies. The hydrogen atom's simplicity offers a powerful analogy for the universe. Imagine scaling up the hydrogen atom to the size of our solar system. The nucleus, a single proton, would be akin to our sun, while the electron would be analogous to Earth. Now imagine our solar system is just one of many, all orbiting a central galactic core. The parallels to the hydrogen atom are striking. The hydrogen atom offers a glimpse into the fundamental nature of our universe. For centuries, scientists debated the true nature of light. Was it a wave rippling through space, or a stream of particles, tiny packets of energy called photons? The answer in the quantum realm is both. Light exhibits both wave-like and particle-like properties. This wave-particle duality is a profound discovery. It challenges our classical intuition, embracing the quantum world's probabilistic nature. Imagine a vast cosmic ocean of quantum possibilities. Galaxies and stars are wave packets, their positions smeared across distances. This is the world of wave-particle duality. Electrons and photons exhibit wave-like behavior. Larger structures might also have wave-like properties. Could this influence galaxy formation? Might it affect dark matter and dark energy? These questions explore quantum weirdness. We've journeyed through the bizarre realm of quantum mechanics. Imagine our vast universe is but a humble atom in a grander structure. This idea challenges us to consider realities nested within realities. The allure of the unknown keeps us searching the cosmic abyss. Could the laws of physics reflect grander principles in a supercosmos? Some physicists propose that if our universe were embedded within a larger structure, we might detect faint echoes from this higher reality as anomalies in the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation provides a snapshot of the cosmos just moments after its birth. If our universe collided with another, it might have left detectable ripples in this primordial radiation. These anomalies remain highly speculative, and separating them from cosmological noise is daunting. The search for these echoes is a testament to our insatiable curiosity and our yearning to understand our place in the cosmos. In the quantum realm, particles dance to a different tune, defying the rigid laws of classical physics. One of the most bizarre phenomena is quantum tunneling, where particles pass through barriers, like ghosts through walls. In the quantum world, a ball could materialize on the other side. This arises from the wave-like nature of particles. A particle's wave function can extend beyond a barrier. The probability decreases with barrier thickness. But what if we scaled up quantum tunneling to cosmic proportions? Could entire stars, held together by gravity, tunnel through vast distances, defying the constraints of space and time? Some theoretical physicists propose that under extreme conditions, such as those found within black holes or in the early universe, quantum tunneling might play a significant role in the evolution of cosmic structures. Imagine stars spontaneously appearing in distant galaxies, or even entire galaxies leaping across the cosmos, leaving behind only the faintest whispers of their previous existence. These possibilities, while highly speculative, ignite our imaginations and challenge us to expand our understanding of the universe's workings. Could quantum tunneling provide a mechanism for faster-than-light travel, allowing us to traverse the vast cosmic ocean and explore realms previously thought unreachable? While such scenarios remain firmly in the realm of science fiction, the study of quantum tunneling on cosmological scales pushes the boundaries of our knowledge and hints at the profound mysteries that still shroud our universe. Quantum entanglement, once dubbed spooky action at a distance by Einstein, is a perplexing quantum phenomenon. It links two particles, no matter the distance, where one state instantaneously influences the other. In the quantum realm, entangled particles are like two sides of the same coin, their fates linked. Measuring one particle's state instantly reveals the other's, even light years apart. Decades of experiments confirm quantum mechanics, making entanglement a well-established aspect of our universe. If two tiny particles can be linked across vast distances, could larger macroscopic objects, even entire galaxies, be subject to the strange laws of quantum entanglement? Could the fate of a star in our galaxy be intertwined with the fate of another star in a distant galaxy, billions of light years away? Extrapolating quantum entanglement to such scales is highly speculative, and the challenges of maintaining entanglement over such vast distances and timescales are immense. However, the possibility, however remote, is tantalizing. Could entanglement provide a deeper connection between distant parts of the universe, a cosmic web linking the fates of stars, galaxies, and even black holes? Could it offer a new perspective on the universe's evolution, where seemingly independent events are subtly intertwined? While these questions remain unanswered, the study of quantum entanglement on cosmological scales opens up new avenues of exploration, pushing the boundaries of our understanding and challenging us to reimagine the very fabric of reality. In the realm of atoms, energy doesn't flow smoothly like a river. Instead, it's more like a staircase with distinct steps. Electrons can only exist at specific energy levels, like standing on one step at a time. They can jump between levels, but can't exist in between. Absorbing energy makes them leap to a higher level. Releasing energy drops them to a lower level. This release often forms light, with color corresponding to the energy difference. In quantum mechanics, the state of an electron within an atom is described by quantum numbers. No two electrons can have the same set of quantum numbers, known as the Pauli exclusion principle. This principle explains why white dwarf stars can only grow so massive before collapsing. Could entire galaxies be governed by similar rules, each occupying a unique quantum state? Perhaps the universe is a grand quantum system, governed by these underlying quantum principles. We often imagine the vacuum of space as completely empty, a cosmic void, but quantum mechanics paints a far more intriguing picture. It suggests that even the emptiest corners of the cosmos are teeming with activity, a bubbling cauldron of virtual particles constantly popping in and out of existence. Imagine a vast dark ocean. On the surface, it appears calm and serene, but dive deeper, and you'll find an entire ecosystem teeming with life unseen from above. This is the quantum foam, a subatomic frenzy where particles borrow energy from the void, fleetingly coming into existence before disappearing back into the ether. These virtual particles aren't just theoretical constructs. They have measurable effects on the real world, influencing the behavior of atoms and the interactions of light and matter. Their existence could hold the key to understanding some of the universe's most perplexing mysteries, particularly the enigmatic nature of dark matter and dark energy. Consider the vast cosmic web, a tapestry of galaxies woven together by gravity. This intricate structure is shaped by the gravitational pull of dark matter. Dark matter holds galaxies together and influences the universe's large-scale structure. It may interact through the quantum realm, exchanging virtual particles. Imagine a cosmic dance floor where dark matter joins the dance, its presence felt, but unseen. The nature of dark matter remains one of the biggest unsolved mysteries in modern physics. Black holes, those cosmic gluttons, consume everything that ventures too close, but beneath the surface, a surprising connection emerges. At the heart of every atom lies the nucleus, bound by the strong nuclear force. Similarly, a black hole's gravity is so strong that nothing, not even light, can escape. Both are defined by immense density within a small volume. Imagine compressing the Earth to the size of a marble. That's the kind of density we're talking about with black holes. The event horizon of a black hole shares similarities with the boundary of an atomic nucleus. One of the most perplexing puzzles in astrophysics is the black hole information paradox. According to quantum mechanics, information can never be truly destroyed. Yet when an object falls into a black hole, it seems to vanish from existence. Some physicists believe the information is encoded on the event horizon, like a hologram. Could the behavior of atoms hold clues to unraveling this cosmic conundrum? From the smallest atoms to the most massive black holes, we've journeyed through the cosmos, exploring the universe's grand tapestry. The laws of physics govern atoms and shape stars and galaxies. Our universe might be one atom in a grander cosmos. We've delved into dark matter and dark energy. How does this change your view of our place in the universe? Continue exploring the wonders of quantum physics and the universe.